What this device really is a tunable optical grating, and the problem that they are trying to overcome with this is to, in optical fiber communications, you typically have a lot of different, your data is transmitted down a single fiber at discrete frequencies. And so what this device is attempting to do is to be able to selectively filter out certain frequencies, allowing the rest to continue at certain points. So what this device needs to do then is to be able to selectively filter specific wavelengths in optical fiber transmissions. The added functionality for this device compared to state of the art at the time was that the grating that this device can actually be tuned to filter out any specific wavelength that you want. So just some gratings that we all we're familiar with. So these are the transmission grating, and we're pretty familiar with how this works in terms of based on the grating, the spacing of the grating, how the light is refracted. Here we have a reflective grating. Now this device is based on a reflective grating, and what this device will be able to do is to it's a device which is utilizes a Surface Acoustic Wave device, which is referred to as SAW devices. They have many different uses, but one of them is that they have come up with in this patent is to be able to, with this Surface Acoustic Wave device, to vary the pitch of a reflective grating. And by doing that, they can you can pick out a certain frequency of light that you want by whatever the pitch that you tune into the grating. So in optical fiber communications, basically what you have is, as I mentioned earlier, is multiple frequencies traveling down a single fiber. Typically, one of the ways they do this is with this device here, which is a planar light wave device, a waveguide grating. And this device can take multiple frequencies on one end and multiplex them all into a single optical fiber, or the reverse, demux them. So you, at the other end, where you separate them back out. So what this, the patent device that we're looking at here, what this aims to do is on this end of the device, be able to insert this. So it's basically meant for a fiber system. So Steve will go into in a few minutes what the device actually looks like, but it's basically putting this grating in close proximity to this fiber, such that the evanescent field of the mode traveling the fiber can interact with that Surface Acoustic Wave device, and depending on how you tune the device and what the pitch is, you can selectively filter out any of these frequencies that are traveling in the fiber. I think Dan now is going to. Okay, yeah. So, so again, this is a summary of what this would be used for. So, wavelength separation, fiber optics communications, being able to selectively choose which wavelength you want to filter out, and then they didn't do this in this device, but they also claim that you could add another functionality, which is to be able to modulate the optical signal that you're doing by adding a electro-optical overlay, which is typically like a polymer layer on top of that device.
Okay, so initially when they were creating this device, they used a number of metals such as aluminum, quartz, and a number of gold, for example, but they found that using a crystal was more durable, and it was stronger to use over time, and it was just overall it was just more it was just the better metal to use. I shouldn't say metal, but the better product to use over metals, because it was durable. In a nutshell, that's basically what these bullets are telling us. They did use stencils, but over time they would lose their they would quickly lose their features. They would to sum everything up, they would wear out. So.
So, I guess this is a repeat of what both the Dan said. The gratings produce the pitch that's variable, and then the organic material, that MBANP crystal, is what the other Dan was talking about. They claimed it to be an improvement over the traditional lithium niobate, which is used for the piezoelectric, piezoelectric crystals. Basically, it's like quartz. And what Dan was talking about, the fingers on these are stenciled onto the crystal. Now, this is the cross-sectional view of the crystal itself. The entire thing, this unit has the top. It's made of one crystal, and this is not quite a top view. This is actually a bottom view. Think of these as flip over, so this is facing down. So this part of the device is where the surface acoustic wave is generated. The two buds here and these fingers, the wave is going to be generated this way, probably this way. Let me see if I get that right. Well, it doesn't, this particular diagram doesn't show it, but the reason it doesn't show it because this is actually reversible. You could either put input here or put input on the other side. Let me go forward to the next slide to just explain. This particular arrangement is very common in what they call the SAW devices. What you have is the two IDTs, what they call interdigital transducer, and it was invented in 1965. Once this invention allowed a lot of these piezoelectric, uses the piezoelectric effect of the crystal, and by embedding, using litho printing, the electrodes into the crystal, allow you to either using electrical signal to produce acoustic wave and pick up on the other side from using the same transducer. It has many applications. Time delay or motion sensor, anything, your phone, all small appliances would have this little device in there. So what this patent does is it incorporates that. Actually, this patent doesn't have anything new in it. It just uses the old ideas and new materials and new arrangements. So this one unit, the side view looks like this. It is one, they call this the transmission substrate. The entire thing is made of the crystal, like I said. They call this transmission material, the medium. And this in general, this is the surface acoustic wave is created on this side, on the surface of this medium. And then the general purpose is you could shine light through here. It will reflect selectively by tuning the frequency you want to reflect the light to whichever angle you choose. But more specifically, it is designed to be used with optical fibers, like Dan said. And the way they do that is, let's say you lay the optical fiber along this curve. They call these the half coupling, on top of this half coupling. And there's a mistake on that little arrow there, but it's in the patent, so I didn't bother to take it out. But the explanation is that if you lay the fiber on the input wavelengths and the lambda 1 to n, various wavelengths, through the coupling, the transducer would pick out a particular lambda, the output lambda, and And then you could use another pickup coupler. I suppose that's pretty common, so it's not part of pattern. And you can pick out that wavelength and then use optical receiver to do whatever you want with that signal. So that's essentially how this thing works. But go back to the acoustic device itself. This is just an explanation of how of what's going on with the transducer, because all the technology is in that transducer. Like I said, it's really nothing new in these patents, except that they incorporate the transducer with a crystal and made it into this more compact, convenient thing. This is actually about, according to them, about 5 centimeters. So it's really small gadget. And all you have to do is hook the cable, hook your optical fiber onto it, and it'll output the wavelength that you want. So it's very simple. Dan can tell us what you might be able to use these things for.
Again, this is the claims that was copied from the patent. And here you can, this was highlighted in blue. It's distorted because of the projector, but this is of everything that's here. If I was to go through this again, I would be repeating what my colleague said, but again, the advantage is to select a selectively variable manner, which is you can tune the frequency or wavelength. So the next, this is again part of the pattern, and again, advantage is pitch of the grating can be determined by selecting a drive frequency supplied to an interdigital transducer or pair of interdigital transducers. As far as a pair of interdigital transducers in the laser ultrasonic UT or ultrasonic testing, sometimes one transducer is used. 5 megahertz for aluminum, 1 megahertz for coarse steel. For deeper penetration, usually 1 megahertz. Wider penetration, 10 megahertz. For 2 transducers, they use the pitch catch method, and that uses 2 transducers. So that's one instance of using 2 transducers. Another real world scenario for using a sensor or advanced sensing, so to speak, is using a laser Doppler vibrometer to detect landmines. It may seem as if I'm deviating from the subject, but it's still using the same principle of sensing. Even though it's not in the pattern, I just want to make it more clear. So using sound waves and detecting the frequency and amplitude from the laser vibrometer. To the far, your far right is C-scan showing the landmine that's below the surface. Also, it's used to find defects in composite materials. Composite materials is becoming more common nowadays. The drones use composite. A lot of the aircrafts. As a matter of fact, 2 weeks ago, Boeing got some offers to make the Dreamliner 777X. The wings are going to be composite, and they have to be tested using various sound and laser ultrasonic techniques using sensors. But this basically shows surface acoustic wave signals, show A-scan interpretation And also over here it shows pore consolidation. So it's two different materials showing different defects. So you get different interpretations, but using surface area acoustic waves. Also, this is another C-scan, flaw detection due to discontinuities in substrate or materials. I should say this is from a Reese NDT company in Austria. And that's used to detect, using acoustic waves to detect flaws in anisotropic materials, meaning that the physical and mechanical properties vary by orientation. And by the way, piezoelectric, piezo is from the Greek word, it's a Greek word that means to press. So basically you press to get a reaction and an electric charge. So that's why you have the word piezoelectric. And thanks for your time.